next one is another tool for analyzing different types of functions. And we've already been introduced this on a simpler level, but we're now going to look at it more abstractly. And this is something called, second tool we're looking at is polar coordinates. This is what will take up the remaining time today, and hopefully we'll finish everything. If we don't, we'll be able to look at it separately. Well, we're used to the XY coordinates, you know, the Cartesian or the rectangular coordinate system. That's what we're used to. Well, there are certain phenomena out there in the world that don't follow this. Like if you're looking just in a plane and you have some electron, you have an electron in a plane, well, everything emanates from that electron. If it's just in a plane, if you're just concerned about the plane, in a polar way, in a radial fashion. So the field generated by that goes out radially. So there are some phenomena, many phenomena in the world, that we need a different way of identifying points in the plane. Rather than just giving an XY coordinate to identify a point, we might want to identify a point on, you know, in this radial thing, some radial distance out, and perhaps some angle that we specify. And that's what a polar coordinate system does. Instead of sticking strictly with this rectangular, we introduce a new sort of coordinate system. Now the problem with this is, unlike this, one coordinate per point. Here you have infinitely many coordinates per point, and we'll talk about that. So it's not unique. The representation you get is not unique like it is for the rectangular. You don't mix it up for the rectangular coordinate system like you can with the polar. Okay, so let's take a look at that. Let's introduce that, and here I'm going to take us over to the textbook so I don't have to write all these pictures out because it's kind of problematic to do that. So let's take a look at that, and we'll introduce this idea of an alternative way of locating points in the plane. Not using an X and Y coordinate system, but instead using a polar coordinate system. So here it is in the textbook, and I think this is page 302. What you end up creating is a ring of circles, concentric circles of radii 1, 2, 3, etc. Just like on your number line, you put the numbers 1, 2, 3. Now it's the radii that extend out from the center. And then you have along the horizontal, that's our reference line, and that's my angle that I'm going to be using. And that angle there is 0 degrees. And then you just keep rotating around. You can go, you know, 15 degrees, 30, 45, 60, etc. However you want to set this up. Now, this is one way of representing my polar coordinate. I'm given a radius, which is all those concentric circles of varying radii, as well as an angle representation. So, like for example, say I want to represent the point that's 2 units out with an angle of 45 degrees. So I specify from the center, R has a radius 2, and I go up 45 degrees, and that's my point. And how am I going to represent it? Well, instead of X, Y, I'm going to represent that as R theta. So that's the difference. Instead of X and Y, I'm going to be using the radius R and the angle that I am changing from the horizontal. Okay, so that's that point. Let's take a look at so it's kind of like back to this unit circle idea. Instead, we're not at a unit circle, a circle of radius 2 now. But the unit circle, as you can see that we talked about, is still applicable, or a circle is very applicable. That's why I like that concept. If you get that down, it'll help you analyze and understand so many different phenomena. Now, I mentioned that it's not necessarily unique. So, for example, say I wanted to plot this point over here. 2.5 at the angle 7 pi over 6. Okay, so I go, the radius, I go out 2.5. So here's my 2.5, and then I have to rotate it around. Well, here it is, 6. Each of these is pi over 6, and I get 6 pi over 6, and then one more pi over 6, so it puts me at this location in my r theta plane now. And that's what it is. It's the r theta plane. So I'm identifying the location of that point as a radius of 2.5 and an angle from my horizontal of 7 pi over 6 degrees. But that's not necessarily unique. Meaning I could add on another, 2 pi. I could go all the way around 2 pi units. Well, 2 pi is equivalent to 12 pi over 6. So instead of just 7 pi over 6, 19 pi over 6 would also give me the same value. I could go another 2 pi around, and I would get 61, etc., etc. But I could also, if I wanted to, rotate in the opposite direction. So I could take my angle being negative if I wanted to, and over here I go from this, now I go in a clockwise fashion, and that is a negative 5 pi over 6. So you can see over here, I could also represent that with a radius of 2.5, but an angle of negative 5 pi over 6. Or I could then subtract another 12 pi over 6, and that could be written as negative 17 pi over 6. It's not unique. So on a test, you can represent it many ways, differently than others, and still get the same answer. It could be the same answer. There's one additional complexity over here. In some sense, we can think of R should always be a positive quantity, but in many cases, when you're plotting graphs, we allow it to be negative. What does a negative radius mean? Well, if, for example, let's take this simple case over here. So this is R is equal to 2, and theta is equal to pi over 4. If I was going to represent R equal to negative 2 and pi over 4, what I would do is, instead of the point being here, it would go to the opposite side of that circle, and it would be there. It would still be an angle of pi over 4, but R would now be negative. What happens when you change the sign of R? It flips to the other quadrant over here. So if it's in quadrant 1, it flips to quadrant 3, quadrant 2 to 4. It just reverses. The negative R goes in the opposite direction, as opposed to emanating out in that positive angles. It takes that same angle, pi over 4, but goes in the opposite direction. So that also explains why we can have these representations. I could go negative 2.5, and my angle is pi over 6. So where would that be? Well, it would be, here's my 2.5 at pi over 6. But since it's the negative of 2.5, I go in that opposite direction along that same angle here of pi over 6. So it can get confusing. So that's the whole thing. We now have this new set of coordinate systems. And you got to be careful whether things are positive or not. Okay, I think that's enough for in the textbook, and you can kind of look at some of the applications there. But now we've introduced our polar coordinates via the textbook. You can see the complexity there. It's not as basic and easy as the rectangular, where you get a single x comma y coordinate. Here we can have infinitely many to represent any point in there. It can go around this way. R can be negative. I flip the opposite direction. So it has a lot of complications. But what it brings is the ability to analyze different phenomena much more easily. And for those that do stay on and go into the higher mathematics and engineering, this is going to be extremely important. We're going to change coordinate systems when we start solving not algebraic equations, but things called differential equations and partial differential equations. It gets much more complicated. You'll see a little bit more of this when you get to calculus 3. Not as much in calculus 1 and 2, a little bit, but mostly in calculus 3 when we start to analyze things. And not only do we go to polar, we introduce something new called spherical coordinates. So we'll talk about it. We won't talk about that, but you will see that later. Okay, so what do I need to be able to do when I'm given polar coordinates? So what you need to be able to do is do the following. So our objectives here are very simple. One, given a polar form, given an r comma theta, you need to be able to plot that point in a polar graph. Just as we've shown on a previous example. So given r and theta, plot it. The second thing you need to be able to do is, given a point on the graph, find its r comma theta, its ordered pair to identify its location. So given a point on a graph, on a polar graph, so you got something like, all these things emanating out over here, and all these circles, and say, put it over here, can you then determine, find its location, r and theta. But as I said, this is not unique. Now, the best way of doing it is to keep r positive and just go rotate theta in a counterclockwise fashion and pick that smallest angle. But that's not a necessary thing. And when we start to graph, or when when we start to graph, or when Desmo starts to graph things, they change the sign of these points, and they have to kind of keep track of everything there. So you have to kind of keep track of this, even though you say, well, why can't I just always pick R positive and pick that? It's not always that case. So that's what you should be able to do. And you'll see some problems on that. Okay. That's fairly basic. I don't think I'll go into that much. We'll have you try some problems. If you have some difficulties, we will go over them. Let's take a look at what's going to take up probably most of our time in this second set of objectives. We have two coordinate systems now. So now we have another objective because we have the two different coordinate systems, and we need to be able to convert between the two. So that's our objective. Convert between polar and rectangular coordinates. And that's what we're going to focus our attention on. We have these two, and can I convert back and forth between them at a point level and also at a function level. So we're going to do this, convert from point to point and function to function. So how do we do this? Okay, let's take a look back to our unit circle. You notice I've been using the unit circle all throughout. That's why I started with it, because it's something that it helps you all throughout. And let's draw a unit circle over here. And typically we drew that on a rectangular coordinate system. Remember that. And pick any point on that unit circle. And we kind of gave that in terms of this angle theta. And the x-coordinate, this is the point, I'll put two coordinates, x comma y. And we also said, well, that is for the unit circle, it was just, cosine theta comma sine theta. And that's how we identified that point. Now, we could go beyond the unit circle if we wanted to. We saw that. That's our unit circle. But we could expand it beyond the unit circle. And then we have an r comma theta. You kind of see partly there the polar coordinates kind of trying to expose themselves and come out in this sort of formulation. Because you could go beyond the unit circle and now go out Here's my circle of radius 1, but you could go out to a circle of radius, say, 2. And might have something that looks like this. And that's the point I'm looking at. And I would represent that with this distance r, the distance out from the origin, which is 2 in this case. And I could represent it as 2 times the cosine of this angle theta. And we kind of showed that early on, or 2 times the sine of theta. So, and that's also equivalent to that point in Cartesian coordinates of x comma y. Okay. This is going to form the backbone of how we do conversions. Okay? In general, if I don't know what that is, I'd say my x comma y can transform into, that's a radius 2, so I'll write that as r, and we have a comma cosine theta. That's my x. Remember, x is r cosine theta, r sine theta. Now, these are not transformed. These are actually equal. So x comma y, this is still in rectangular coordinates. This is rectangular, even though we're using r and theta over here. To transform it into true polar, then I'd have to say this is equivalent to an r comma theta. This is polar, that's rectangular. Rectangular, still rectangular, but I'm using some of the polar notation here, and then I transform it into a true polar form. But that kind of gives us a connection between the two. And I'll come back and do that. So what do we have? What have we established? Well, I have the relations now that are important. One is x is equivalent to r cosine theta. From there, y is r sine theta, right? From this whole idea that I just developed here. Now, that tells me how to, if I'm given an r and a theta, it tells me how to find x and y. So these relations allow me to go from polar to rectangular. So this will, and I'll show you in a second. This goes from polar, meaning an r and a theta, to my rectangular, meaning x comma y. Well, I need to go the opposite direction as well. Well, we can do that as well. Let's take a look at that picture over here. I'm just going to now make this more generic. And you're going to kind of see the approach that you have to take. So if I go and kind of just draw my, any sort of generic polar form over here. And let's say I do have some sort of a point on that grid over here. It comes out at some length r, and it has some angle theta. Again, always from the horizontal. Well, what can I do? Well, I have a triangle, so I can drop my perpendicular over here, and I create a right triangle. Okay, so this distance over here, if this, I could also superimpose on here. So I have my polar, but I could also superimpose my Cartesian on here. I'm laying one grid on top of the other. I have my r and theta as well as my x and y. Well, if I notice here, this is my height y. That is my length x. If I superimpose on top of that my rectangular. So what I have Pythagorean's identity. That tells me over here that r squared is x squared plus y squared, right? That's how I can find my r in terms of x and y. Or, if I want to take r to be positive, which you don't always have to, r is the square root of x squared plus y squared. That's also my distance formula, the distance to the origin. Okay, now we have the angle theta. Well, what relationship do we have that might work with that? Well, we have the following. We have that the tangent of theta, okay, is equal to, remember this theta, is opposite over the adjacent, TOA. So it's equal to y over x. Remember, it's like a TOA. Here's the angle theta, opposite over the adjacent. Or I can take the arctangent of both sides and get theta is equal to the inverse tangent of y over x. However, this is a little bit of a problem. Why is that? Well, when I use this, remember the arctangent of any value has its range is between minus 90 and, the output is the range, and plus 90 degrees. It'll only give me angles in this region over here. So if my point, so it'll be accurate in these regions here. So as long as I'm in, let's put it in green, as long as my point lies somewhere in this range over here, I can use that directly. However, if I'm in quadrant 4, it's always going to give me a negative angle. It's only going to give me exactly what I want with a positive angle and a positive r in quadrant 1. If the point comes over here, it's going to give me the value that's over here, the angle over here, and then I have to add 180 degrees to it. If, however, the point occurs here, it's going to give me the positive, and then I'm going to also have to add 180 degrees. So if it's not in quadrant 1 or 4, I have to do extra work. Even in quadrant 4, you can use a negative angle. There's nothing wrong with that, but sometimes you might want that positive angle. But if it's in quadrant 2 or 3, because the arctangent, its range is not in that range of values, I have to do extra work. So here and here is extra work that you have to do. So that's what makes it a little more awkward. So in addition to those relations, I now have these relations. With the caveat that I just said about the arctangent. That's going to require some additional work, if you will. So this one set of relations, and here's our other set of relations. We have r is the square root of x squared plus y squared, and theta is equal to the arctangent of y over x, with that disclaimer. It only will give me values between minus 90 and plus 90. Now, these relations will allow us to go from x and y's to r and theta. If I plug in an x and a y, I can get an r. Plug in a y and an x over here, I can get a theta. So this is convergence from rectangular x comma y to polar r comma theta. Okay, so let's take a look at that and see how well we can do. Let's do it, the two types of conversions. This is what we're going to look at. So how do we apply those? This is the key. These are the things that you really want to definitely commit these to memory. They will come up time and time again throughout your mathematics career and your engineering and science career. Okay, so two types of conversions. One type of conversion is point-to-point conversion. given one point, find the other in the other coordinate system. Point-to-point conversions. So let's, for example, say I have in my rectangular, let's do the other one. Say I have, let's see, other case is easy. Say I have bipolar, and I'm giving my value that R is equal to 5 and theta is equal to pi over 3. And I want to convert that into my rectangular. So I'm going to use these sort of conversions. So what do? Right from here, I have x is equal to R. I'll write it over R cosine theta. And y is equal to R sine theta. So I can plug it in. So x is equal to 5 times the cosine of pi over 3. Y is equal to 5 times the sine of pi over 3. And what do? Well, we like to go, if we can, go to the exact values. If you can't, then you have to use your calculator and approximate value over here. But this is 60 degrees. And again, think of your unit circle. Here I am at, my angle is 60 degrees. The cosine, this is a half, so it's equal to x 5 times on the unit circle, that's 1/2. And for the y, that's the square root of 3 over 2. So it's equal to 5 times square root of 3 over 2. So my xy coordinate that's associated with that r theta is now 5/2, comma, 5 square root of 3 over 2. So I changed from r theta to xy. Very simple. Okay, now let's do the other set of equations over here. This is where it gets a little more problematic. And let's do this one as an approximate one. Say this one turns out to be approximately equal. So now here's the second one. This is example, A, we'll call that, and here's example B. So now I will have an x comma y, which let's say it's given to us. Let's pick an easy. I'll pick an easy one. 2 comma 3. This is not going to give us exact angles. It's going to give us something approximate. And we now want to go to my r comma theta. So that's my x comma y is given like that, and I'd like to convert this into an r comma theta. What do? Well, I know r is just equal to the square root of x squared plus y squared. Okay, so I can do that very simply. Square root of 4 plus 9, so r is equal to the square root of 13. Well, that will leave as exact. Now I want to get my angle theta. Okay, so my angle theta is equal to the arctangent of y over x. And let's understand which quadrant that's in. So when you do this, you have to figure out where am I. Well, here I am. I'm in quadrant 1. So, okay, everything's safe. I don't have to worry about that angle. It's going to give me the angle that will work out precisely. So my angle theta is equal to the arctangent of 3 over 2. Now, there is no exact value for that. So for that, we have to go to our calculator. And what I usually like to do is I'll set my theta for degrees and then determine whether or not I can, whether I desire to do it separately. So let's go to a calculator, see if I got one. Okay, there we go. So here we have our calculator. Turn it on over here. What I might do, let me just check. I like to put my mode. I'll set it for degrees. It's a little bit easier to calculate because it's hard for me to, recognize a radian measure of say, 45 degrees, which is, 3.14 divided by 4. So it's a little bit harder to see. And then I'll go over here. Let's quit that, and then just take my second function. Arctangent 3 divided by 2 is just 1.5, and it's going to give me the approximate angle in degrees. So it's 57 6.3 degrees approximately. So if I come back now, I can rewrite this as my theta is approximately 56.3 degrees. I usually like to use degree measure here because it's a little more, indicative. It's hard to see 6.2, 8 is 360 degrees. So what is my r and theta? Well, it's approximately equal to square root of 13 is exact. The angle theta is 56.3 degrees. Oftentimes you just get approximation. Now what if I just change this very slightly? So let's say I put this over here. Put that negative. Well, notice what happens. This doesn't change. Square that, I get positive. So that's the same thing. But instead of here, I am at this location right here. Well, if I plug in over here, what I'm going to get? I'm going to get theta is equal to the arctangent. Y is 3, but now x is negative 2. So let's do the same thing and see what we get using our, again, our calculator. So now I'm going to take the arctangent, but now I'm going to put the negative of 1.5. And what will the arctangent do? It's going to give me an angle of negative 56.3 degrees. Okay, so that's what I have. So it put me over here. That's where it put me. That's not the angle I need. I want to get this angle over here. So what do I have to do? I have to add, this kind of gives me theta is approximately a negative 56.3 degrees. So what do I need to do? I need to add 180 degrees to that. And that'll give me the correct angle. So I add 180 to that. So, or 180 minus 56.3. So 180 minus 56.3. And that'll give me 123.7 degrees. So that's the angle I want over here, 123.7 degrees. So for that, it would be approximately equal to square root of 13, same r, but now it's going to be approximately 123.7 degrees. So you can kind of see what you have to do to get that. Okay, we're out of time today. We'll stop here. Converting a Cartesian expression into a polar expression or function, if we wanted to write it out as a function, or, vice versa, just the opposite, polar to Cartesian. So let's kind of take a look at what we mean by that. And here we're going to be using essentially these formulations. So we have x is equal to r cosine theta, y is equal to r sine theta. This is what we use when we want to convert from polar to Cartesian. So it's from, just as we did for the points, polar to Cartesian. Or if you want to flip it around the other way, if you want to go from Cartesian to polar, we're going to be using my r is x squared plus y squared, and my theta, with some caveats and some modifications over here, is you can put as the arctangent of y over x. I'm going to change this a little bit. And if I take the tangent of both sides, so if I take the tangent of both sides, I get my, if you're given in something else, it might be, we'll still use a combination ease. You could also say tangent of theta is y over x. That's another possibility that we might use. So kind of be careful of what we're going to be using for this one. Coming from Cartesian to polar, as you can might well imagine, just as in the other case, is a little bit more complicated than polar to Cartesian. So what do I mean by that? So let's take a very simple equation, or maybe not so simple, an expression, polar coordinates. So let's take the first thing. Say I have x squared plus y squared is equal to, 4. And I'd like to change from my Cartesian representation to polar representation. So what do? So I'm going to go from Cartesian. I'm talking and writing in reverse. This is polar to Cartesian. Keep me awake. Talking and writing. So here's my Cartesian. I'm going to make the change of variables where x is r cosine theta. So I replace that, r cosine theta, quantity squared. Y is r sine theta, quantity squared, is equal to 4. Let's square this out. R squared cosine squared theta plus r squared sine squared theta is equal to 4. Factor out an r squared to get r squared cosine squared theta plus sine squared theta is equal to 4. Well, what is this cosine squared and the sine squared? Well, that's just 1. So that just gives me r squared is equal to 4. Or I could actually take the square root of that and say r is equal to 2. Now, what is this? Well, that's an equation of a circle of radius 2. What is this? Well, that's also the same thing. Equation of a circle of radius 2. So if I go to polar coordinates over here, if I go out 2 units, there's 1, there's 2. This tells me theta can be anything. Theta is anything, but r has to be consistently equal to 2. Gives me the same exact thing, but in my polar versus my rectangular. You can see where this is so much easier. In this new coordinate system, it's equal to a constant. Whereas here, it's more problematic. And to graph this on most calculators in this mode, it's kind of hard to do. You have to solve it for y. And if you want to graph this on your calculator, not so much on Desmos, but on the calculators you have, it's a little more problematic. I'd have to say y is equal to the plus or minus the square root of 4 minus x squared. Plus will give me the top half of the circle, minus will give me the bottom half of the circle. And I have to do it in pieces on an HP calculator. Or, TI calculator. But I can do this exactly, and we have the software packages that you see. So that's an example. Let me give you another one now. Let's try this one. And then we'll go to the other, from polar to Cartesian. This is a change of variables that you need to be comfortable doing. Especially when you get to the calculus, you'll be doing change of variables often, but you just kind of need to be comfortable with that. So I'll give you one to try. So see if you can recast or rewrite that equation in polar form. Let's see what you get over here. I'll do it in my head and see if I can get it right or not. not equal to a constant. It depends upon the angle theta. I think that's what I did in my head, make sure I got it correct. Anyone want to see that worked out? Okay, so let's kind of plug that in and see what we get over here. And then we'll take a look at Desmos and see how they give us the same equivalent representation. Okay, so what would I do? I'm going to use x is r cosine theta and y is equal to r sine theta. I'm going to plug those in for my x's and my y. So doing that, I'm going to get r squared cosine squared theta over here plus 2r cosine theta minus 1 plus y is r squared sine squared theta is equal to 0. Okay, what I have over here, I notice I have an r squared and an r squared. I can combine those, but notice cosine squared plus sine squared just going to give me, I have another, I'm missing something, yep. I'm missing a 1 over here. That's my typo. So when I do that over here, I can combine those together and get simply r squared. Let me do it. Cosine squared theta plus sine squared theta plus 2r cosine theta minus 1 equals to 0. This is just 1, so I get, and it's something that gives me 1 over r. Yeah, gotta be careful. But don't quite get it as nice as that one. Okay, so what happens over here? I get r squared times 1 plus 2r cosine theta is equal to 1. That's what I'd have to leave it as. And this will give me the same graph as that particular function. So when I did in my head, I forgot to the 1, and I forgot the 1 I was dividing by the r. So you can't do that. You could, but then it would be a 1 over r. It's nice to have r equal to something if you can, but that's not always possible. Now let's plug it into the calculator and see what is that the graph of. Let's try using our Desmos. I'm going to try in the last test to see if we can incorporate Desmos into the test. Let's see how well that will go, though. Okay, so let me try this now. So if we can put the first one up there that we have, which is x squared plus x squared plus 2x minus 1 plus y squared. So you can see there's a circle that's shifted kind of down the x-axis. Let's take a look at our other representation. We have r squared plus 2r cosine theta. You just type in theta is equal to 1. And let's see. It's not liking that. I guess it's not. I guess I have to shift over to polar coordinates over here. R squared plus 2r cosine theta is equal to 1. What's that? Oh, the polar equations must be linear in R, so they won't do it. That's kind of, I didn't know it had limitations. So it can only do the linear equations in R, not these ones that are not linear. So that's kind of a problem there. If this was 0 over here, I could do it. Meaning I could do this. It's not going to give me the same graph. That's nice to know the limitations there. Put that 0, and then I get rid of that R and this R. And that will give me something there. So it's similar to it, but it's not the same, graph. But you kind of see it. It seems to be close. And not quite. So it just shifts it a little bit there. Okay. But anyway, it's good to play around with these things to see what's happening. So it has to be linear in R, so you have to be able to specifically solve for R for that to work out explicitly. Let's see, Colin, do you have your hand raised? Okay. Did want to make sure you didn't have a question. My hand raised over there as that is. Okay, we're back over here. So there it is. There's our representation. But again, it's a little bit hard. Now what we could do is we could complete the square on this and solve it for plus and minus R, and I could still get it. Okay, but that's how we change from my Cartesian to my polar form. Let's try another one. Let me try another one. I'll make this one a little bit easier. And then we'll go the other way. So try this. There I have my x squared minus 4y plus y squared is equal to 0. I'd like you to change that into polar coordinates. And we'll graph it both in our Desmos. I'll put both of them in. While you're working on that, I will set up Desmos so I don't have to do it here indirectly. Now try and solve it for R if you can. In this case, I set up so you can. Like R is equal to 4 times the sine of theta. Does anyone want to see how I got that? Okay, so I'm plugging in x is our cosine theta, y is our sine theta, so let's do that. So x gives me r squared cosine squared theta minus 4r sine theta, that's my y is r sine theta, plus r squared sine squared theta is equal to 0. Now these two I can combine together to just give me r squared. Cosine squared plus sine squared is 1. I get r squared minus 4r sine theta equal to 0. Move this over. R squared is 4r sine of theta. Then I can simply divide both sides by r. And I get r is just 4 times the sine of theta. Now, if I go to my Desmos, if I have it solved for r, that should indeed show me that they are the same, or give the same graphs. Let's kind of show that. So here's my Desmos. Here's my, x squared minus 4y plus y squared. There it is. It's my circle over here. And it's a sort of radius to shift it to this point. Now, here's r is equal to 4 sine of theta. And if I now highlight that to draw it, there it goes. It's the same exact graph. Now you can actually control that variable theta. I'm going all the way around to 2 pi, so in that case we cover everything. If we only go to pi, let's see what it does. Go from 0 to pi. Okay, so it does. It is going the whole thing. Yeah, so it would be just half of that. Pi divided by 2. Yeah, it just gives me half. So just going pi, because it's a 4 over here. This is 4. It brings me half of it is pi over 2, and then the other half is the other pi over 2. So I only need pi to cover the entire graph of that. Okay, so that shows you how to go from there. You can do it on your calculators. Let's show you that process over here. It's a little bit harder to do. You can't do Cartesian and polar at the same time. So that's the problem with that. But if I come over here, and if I want to go to my mode over here, and if I look at the function mode, it has polar mode. So let me go down here, and I'm going to leave it in degrees, but then show you how to go to the next button down here and go to polar mode. Okay, hit enter. And then when I come over here and hit my y value, it's going to be r's and theta over here. So r is equal to 4 times the sine of theta. So I'll put that 4 times the sine of, and there's my theta over here. Now for my window, my theta, theta is always back to radians. Oh, okay, I see that. Let me go back and show that again. So here it is. If I go and I can kind of go to my mode over here, go down to where it says function, over to polar, highlight that, quit that, and then I can plug in my function. Now notice I have an r over here. Put 4 sine, and when I hit the angle over here, it gives me theta. But the window is always set up for, in this case, radian measure. So what I should do is, let's take, we only need 180 degrees, but say we put 360, because now this is going to be in terms of my degrees. And let's go in increments of, say, 1 degree or something like that. And x max, it's probably my y max there. That's probably good enough. Let's take a look at that. Let's graph it and see what happens. And so it's kind of, I need to go the other direction, so it's not giving me that. So now I need to see the whole thing. That's why it's a little more awkward over here. My x max, I must have 0 over there. So let me take my window. X min was 0. Okay, so here, make it as, make it minus 8 to 8. And minus 8 to 8. And just so we can see. So it's going to be a circle that's kind of squashed because my aspect ratio is not set correctly. It looks more like something we call, at the end of the course, we'll talk about an ellipse, but it's actually a circle. So you can do it on these calculators. It's just a little more problematic to do it. And you can't put the polar and the rectangular on the same graph. And that can be sort of problematic. Okay, so that's how we go from Cartesian to polar. Let's go the other way. Now, say for example, I have, let me give you some example over here. That's too bad. R is equal to the sine of 2 theta. Okay, that's what I have. And I'd like to change this into my, if you will, Cartesian form. So what do I have? What are my tools for that? Well, over here I have my r squared is x squared plus y squared, which corresponds to r is the square root of x squared plus y squared. So I have that up my sleeve. I also have that my, if I wanted to, I could do it this way. remember I have x is equal to r cosine theta. Well, I could turn around and solve that for cosine theta. So cosine theta is x over r. As I said, this one's more complicated. I also have the relationship y is equal to r sine theta. Well, I could flip this around and say sine of theta is equal to y over r. And I also have that the arctangent of y over x is equal to the angle theta. That's another thing I have as well. All of these are suitable. Let's see what we have over here. First thing I would do is I'd use my trig identity. I'd say, well, sine theta is nothing more than, sine of 2 theta is 2 times the sine of theta times the cosine of theta, right? I'm using that trig identity. Then I can look at over here. Look what I have over here. I have an r over here. I have a sine and a cosine. Well, let's change the sine and cosine using these. I got to get rid of that r and the sine of theta and cosine of theta. So I need to get rid of that. But let's take a look at this. Sine theta is y over r. Okay. Cosine theta is x over r. Okay, let's multiply everything, both sides, by r squared. So I get r cubed is equal to 2 times x times y. I just changed the order, put x first. But what is r? Well, r is nothing more than the square root of x squared plus y squared, square rooted, but then I cube it, is equal to 2xy. As you can see, this gets me a much crazier looking representation. And then if I cube that, I can write it this way, that x squared plus y squared, well, this is 1/2 power raised to the 3rd power, so it gives me to the 3/2 power is equal to 2xy. Now, this is virtually impossible to graph on your calculators, but you can graph that on Desmos or some other devices such as GeoGebra. But this, see how easy that is? Let's take a look at what that looks like. What's the picture of that graph? Let's take a look at the picture of that graph and you'll kind of see. Well, I'm going to go back to our Desmos over here. Let me get rid of that, get rid of that. And let's just do r then is equal to sine 2 theta. And you can see it's kind of this 4-leaf rows over here. A very complicated looking structure. Now let's try that other representation. So I have my x squared plus y squared and raise that up to the raise that up to the 1.5 power or 3/2 power, and that's equal to 2xy. And what happens here, it only gives me half of the graph. If I want to get the other one, I would have to put in plus or minus over here. So if I put in, I think if I put in the minus, it gives me the other half. So I have to graph 2 of these to get it to work out. I have to take this one, which is the plus, because I get a plus and minus r. That's the whole thing that happens over here. And if I want the entire graph, I have to put the minus over here. And graphing them both together, the green, if I make this green as well, oops, don't shut that off, but make that green as well, then I would see, I can shut both of those off, and there's my original, we'll turn both of those on, and then I have the other graph. And you can see, it gives you a very elaborate looking graph that you can't do very easily or well using Cartesian coordinate system. That's why, oftentimes better not to use those, but to use polar. So polar can allow you to graph things that are much more elaborate in shape.